Okay, so we're going to talk about dynamic games for a little bit in this section. So I just want to start by motivating why would dynamic games, why would, you might think that's just IO, but you're starting to see this in the human capital life cycle literature. So if you look at most of the work so far, it uses single agent dynamic, and I think that's entirely appropriate. We call that the unitary model. But then there was a jump to something called the collective model that kind of distinguished, like in a couple, the man, the husband and the wife making separate decisions. But what it did is assume there was a Pareto efficient allocation in the family so you could maximize a weighted average of the utility. So then it kind of is very similar to a unitary model. You're maximizing a weighted average of the husband and the wife utility, and the couple is somehow cooperating on the solution. But now we're starting to see more and more models of non-cooperative, where the husband and wife make separate decisions, and they're essentially playing a game within the family. So this is one of the things. Maybe it's a little dodgy. It's not clear. Do you think if you're married, do you think you're playing a game of a non-cooperative game of incomplete information? Most of my colleagues who think marriage is like that are now divorced. But but this is a frontier area. I'm going to summarize some of that. And then now we're even talking about models of individual decision making, that you're playing a game against your future selves or your alter ego, right? There's dual self models where you have a temptation self and then a long run kind of good self that's thinking, don't do that, it's not good for you. But then the greedy current self wants to take an action, and there's this conflict, and there's motivation from neuroscience that actually might have content, and it actually is something that we should think about. Okay, so the unitary model was introduced by Chaparri in 1992, and then Maurizio Mazzocco from his PhD thesis had a paper in 2007, and it's a nice kind of a summary. And then so here, equation one is an example of the unitary model. It's just a family consumption. There may be a family common goods called QT, like collective goods, like a house. You're sharing the house, and it's collective. But then here's the unitary model. There's Pareto weights on the husband utility, and then there's the wife utility, and then there's now you're breaking out the consumptions of the husband and the wife, and so it's still kind of a single agent problem, but with more choices of consumption. But Mauricio observes that you can kind of define a family utility function at any given time. You want to maximize the per period utility of the husband and the wife, the weighted utility, subject to an overall consumption. So there's an within period consumption. How do you allocate between the husband and the wife? And then an intertemporal, how do you consumption save as a family? So now, when we start to look at non-cooperative, there's a very cool paper by Eckstein and Lifshitz in the 2015 IER. And they're now going to look at non-cooperative models of the household. And they're going to look at three kinds of households. One is a classical household, which is models a Stackelberg leader where the wife is a Stackelberg follower. So, the wife kind of makes her decision contingent on what the husband might do. The husband realizes the wife's best response, and then he just chooses what's best for him, taking into the wife's best response to that. And so that's one model. Then they talk about the modern household, and that's a dynamic game between the husband and wife. They're kind of symmetric players, choosing their labor supply every period to maximize their own utilities, but taking into account what the other's going to do, and what the other's going to do is going to affect them. So they're coordinating and they're playing a Nash equilibrium. Now, unlike the collective model, these Nash equilibrium could have an inefficient outcome, that maybe both players are not coordinating and getting a Pareto efficient equilibrium outcome. But then you have the cooperative household where the family really gets together and they avoid those inefficiencies and find the most preferred equilibrium that's Pareto efficient. So this is kind of interesting. They estimated the model and then they use equilibrium selection. So essentially they're estimating the model by simulated method of moments, but they solve the model 3 times under these 3 solutions, right? The classical, the modern, and the cooperative household, and they draw at random some relative in the simulations, certain fraction of the classicals and so on, and then they form the moments and then estimate this along with the probabilities that the households are one of these 3 types. So they're essentially doing an empirical equilibrium selection by seeing what fractions of these 3 kinds of households as types best fit the data. And what they find is that from USPSID data, 50%, 7% of the 1983-84 cohort of newlyweds were classical, Stackelberg. And then, and the hypothesis is everyone's classical is rejected, but the proportion of modern households is 25% and cooperative households is 18%. So I think that's kind of a very interesting study. And what they find also is that in all 3 of these solution concepts, the man's behavior is not really much different. But what's different among the solution concepts is the female's behavior. The female is a quite different labor supply, and that helps identify these 3 different equilibrium concepts. And so they kind of related to social norms and saying that maybe over time, there may be an increase in labor supply of women in modern and cooperative households and so on. So that's just an example of how this is being used in this literature, and where I think that's kind of but they talked about the possibility for multiple equilibria, and they found that they acknowledged it could happen because these simultaneous move games dynamic games can have multiple equilibria, but they reported that they didn't find any at their parameter estimates. They didn't find evidence of it. But there's other ways to model to avoid multiple equilibria, to use alternating move games. Like maybe the husband moves first and then the wife moves, and they move in an alternating fashion. And if you work by backward induction, you can get a nice dynamic programming solution with a unique equilibrium. And it's really not much any different than just solving a single agent problem by backward induction. So there's a paper by Bolus and Seitz. It's more on a darker topic. It's on domestic violence and employment and divorce. And in their model, the women and the husband and the wife are making decisions in an alternating move fashion. And and they get a unique equilibrium and can solve this thing by backward induction. So I'm just going to, we'll post a paper, and it's a little bit of a dark topic. So I think I won't say too much. You don't like to think about men, choosing to abuse. But in their model, the man either chooses to be abusive or not in the marriage. It's, that's kind of a dark thing to think about. So now let's look at individual agents models. And there's a paper by Bernheim, Ray, and Sveltekin called Poverty and Self-Control. And they kind of argue, they use the hyperbolic discounting. We saw work on this earlier in the conference, and hyperbolic discounting is this extra discount parameter beta that makes you time inconsistent, right? So it's like at time 0, you assume that starting from time 1, you're going to have discounting your utility at a rate delta, but then you're a little extra impatient. So your time 0 self says, I want to just consume a little more, but my next period I'll go back to being good and I'll save for the future. But then, at time 1 happens and the same preference repeats itself. You think you're going to go back to being good with discounting a delta, and then you're impatient again. So there's the time 1 self that's also kind of myopic and a little more present biased. And if you actually talk about what's called a sophisticated hyperbolic discounter, see, the naive always is just myopic. They always say, I'm going to be a little greedy today, but my future self will go back, and you just kind of believe your future self is going to be good. But then every period, you're just myopically ignoring the fact that you always keep, you keep violating, and your expectations are incorrect. So a dynamic game is where you realize every future self is going to have this present bias, and you take into account that strategy. Now, when you do that, and you allow for history-dependent strategies, so so in these games, your earlier selves want to kind of discipline the future selves, and by punishment strategies, you get it's like a folk theorem. You get a whole range of equilibria. And so you get actually potentially a continuum of equilibria. So here's an example from a solution of their model. And this is kind of current assets and the amount of assets you leave for tomorrow. And there's a whole range of equilibria between the highest equilibrium savings and the lowest one. And then there's a discontinuity, and this is their kind of poverty trap. If your initial assets are in here, you converge to this poverty floor. Now, what happens up here is that if you're playing the best equilibrium against your future selves, you can actually get asset, and these people can accumulate and save and avoid the poverty trap. So here's an example, and there are multiple equilibria, and very hard to compute this, and progress is being made. But you might just say, do I really, if we're thinking about multiple agents and different agents having multiple, but even if I have multiple equilibria within myself, it starts to really compound. You think, wow, this is really, really hard to do economics, right? Now, there's just different ways to do it. So I'm just going to say there's another way where you can get a unique equilibrium. They're called dual self models. Pessendorfer is also, Wolfgang and Fargoul have some work on this too. There's a paper by Fudenberg and Levine called the dual self model of self-control. And that model also, it has a model where there's a patient long-run player and then a series of myopic short-run players. And basically, the short-run players are making the decisions from time to time. But what the long-run player does is it can effectively create the incentives for the short-run player. So with some effort, it's like, you're about to take that cake and or that last beer, and I shouldn't do it. I'm going to be drunk tomorrow, and I'm going to have a hangover. And then, but your long-run self says, John, don't do that. Don't do that. And if you do that, you're just going to feel really guilty. And then, I say, okay, I'm not going to have that last beer, right? But, it takes effort. For those of you, who have some kind of addiction like smoking or something, it's really, really hard. It takes a lot of effort to stop smoking. It actually is costly. So, for any of us, yeah. So, self-control is a costly thing. It's well known about this. And there's some really, really good work in psychology. There's something called the marshmallow test, right? Where they gave kids a chance to get, you can have one marshmallow right away, but if you wait 15 minutes, you're going to get 2 marshmallows. And what they found in this test, a psychologist called Walter Mischel, is the kids that could self-control and just sit there, because they're sitting in a room all by themselves, and there's that one marshmallow, and there's a timer, but some of them you can see they're just looking and trying to look away, but they really want that marshmallow. And some of them just break down, they grab the marshmallow and gulp it up. But others you can see they're using all these self-control devices, and and then the 2 marshmallows arrive and they're rewarded. And they claim that the kids who did that, who had the better self-control, were more successful in life. Now, it's a little bit controversial, but these are kind of really interesting areas of the self-control. And so there's models, I just want to say there's models of this out there. And these models lead to unique equilibria. Like here's one where, your presence of logarithmic utility. 0 means this the amount of self-control your long-run self exerts. And if you don't do any long-run control, your utility of consumption, S is the saving rate, Y is your income, and the short-run self would just choose to eat everything up now. Okay, but then, so what they model is that you can, with some cost, your long run self can discipline the short run self. And then here they assume some cost function here of doing this. And so the long run self then is choosing a savings rate by exercising a cost. It's costly for the long run self. The long run self can force the short run selves to choose a given savings rate. And so then you get a single agent, kind of a single agent problem for solving the life cycle problem. You avoid the multiple equilibrium. Okay, so this is just a tour just to say this stuff is relevant. But what we're going to talk about now, we're going to switch this to Bertrand price competition. And so and how I'm just going to talk a little bit of how we got into this, but we're going to talk about leapfrogging. And normally I don't do game theory, so I just want to do something a little bit semi-autobiographical just to introduce this, and then we're going to play a little game. It's a leapfrogging game, but and we're going to show today, and Fedor's going to show that we can this leapfrogging game, we can find all of the equilibria, but finding equilibria, even one equilibrium, can be hard in these dynamic games. So so the question is, how do theorists find Markov perfect or a Nash equilibrium? Well, the way I was taught was guess and verify, right? You guess an equilibrium and then you check, is it a best response, right? And the problem is like, how do you teach someone to guess, right? So this was my game theory teacher when I was at MIT, Eric Maskin. And, when I went to MIT, first of all, just to tell you, I expected to flunk out. I went there and I thought everyone is so much smarter than me, I'm just not going to be able to get through that place. Well, I enrolled, I said, I'll just take a chance. I'm probably going to flunk out. Well, I did make it through all classes except his class, right? So I got a B minus, which is like getting an F at MIT. Getting a B minus is like failing a course. So but just in my defense, here's my classmates: Tim Kehoe, David Levine, Drew Fudenberg, and John Tirole. And what was really annoying is that I could verify. I learned the Nash equilibrium. I could verify whether it's an equilibrium or not. But I just didn't have a good skill at guessing, and so these guys could guess. And what was really annoying is that he would give these impossible problem sets, and I'm sure he didn't even know the answer. Eric was probably trying to do news. He knew he had some smart students, so he would just write a question he probably didn't even know the answer to. These guys would find out the answer in probably a very short amount of time. And then I'm guessing, and nothing's working, and I'm working late in the night. And these other guys are running around playing Dungeons and Dragons all night in the basement of E52, where we were getting our PhD. So it was just so annoying, and so that was and so I think after that I decided I'm not going to do any game theory for the rest of my life. I'm not a game theorist, and only smarter people can do that. So fast forward about 25 years. This is a beach in Australia, and this is a true story. It's like 1999, January 1999, and it's called the Sunshine Coast in Australia. And there's literally two executives walking on the beach. So it's like a bad joke, of two executives meeting each other on the beach, and collusion. So we call this as collusion on the beach. These executives were fierce competitors. This is one of them, Peter Brown. He's Amcor. Amcor makes cardboard in Australia. It's like cardboard's a duopoly. So one company is called Amcor, the other is called Visi. And so this is Harry Debney of Visi. And this is a cardboard box, or they call it corrugated fiber products. And they colluded. And they started, to collude for this a number of years. And so these, when they started to collude, basically the chairman of the boards got involved, and this is Amcor's chairman of the board, and then this is the owner of Visi. His name is Richard Pratt. So so this comes, and eventually those collusion got found out, And then an economic expert had to be hired to calculate damages. So what were the damages but for, if there had been no collusion, what would have been the price of cardboard? And somehow I got chosen to be the expert for the defense. So there was a company that was harmed by this called Cadbury. They use a lot of cardboard. You know, Cadbury makes chocolates and the soft drinks, and they used a lot of cardboard, and they sued for damages. And I got chosen as economic expert to estimate what would the price of cardboard been but for the collusion. Now, so how much time? I'm a little bit over time, but no, I don't need 10 minutes here. Basically, here's the case that between 2000 and 2005, they colluded. These are kind of facts. In fact, they colluded, and they would the lieutenants who just disciplined that actually enforced the collusion. They met in bars, and one of them would wear a tape recording just to protect himself. And so I could listen to the actual meetings in the bars where they're arguing about, you know, how they're gonna divide up the spoils of the collusion. So it's just completely incontrovertible that there was this collusion, and so it's just a amount of figuring out what the but-for price what would it have been if they hadn't colluded. Now, my opinion is that the but-for prices would have been described by Bertrand price competition with some leapfrogging competition. And the reason I got to that is this is Amcor's, the key input to cardboard is paper, and they have recycled and new paper. And this is called the Botany plant. If you fly into Sydney, as you're approaching the airport, you can actually see this plant from it's not far from the runway. And so there's this old plant that they had that were built way back in the 50s and 60s, which is a huge set of buildings that grinds up the pulp and the recycled paper to make new paper, which is the main ingredient for cardboard. And these are really old, environmentally inefficient production process. It would pollute the Botany Bay. It used a lot of electricity and so on, environmentally very unfriendly. And so I had found a memo in my research that in around 1997, they realized that they need to replace this plant, and they were planning a new plant called B9 that would have gone right here, that was way, way more efficient. And they had really incredibly detailed engineering cost estimates about how they could leapfrog Visi to become the low-cost producer of cardboard. So Visi had leapfrogged them, and they were low cost, and they were going to then leapfrog Visi, and they estimated how much time it would take for Visi to come back and leapfrog them again. And they said this $400 million investment was worth it because they would have the low cost for long enough to be the low-cost leader to make it a justifiable investment. And they actually had rates of return and everything worked out. So I saw that and I said, this is the smoking gun, because then this is 1997, they had this and they were planning to do this plant. But then there's this meeting on the beach in 1999. And then after that, in the paper trail, no more discussion of B9. It just disappeared, right? Like, why would, if this was such a great investment, why would they would just drop it? Well, I hypothesized that they didn't need to build this anymore because they're going to raise the prices. They don't have to compete by leapfrog anymore. They're going to compete by non-compete by collusion. So that was my case. And in the end, we won the case, but the other side, is brutal. If you're an expert, the other side attacks you and says your expert is dumb. And what they said about me is they said, well, everyone knows there's going to be tacit collusion, right? That if you don't have explicit collusion, you never have Bertrand competition. You have tacit collusion. And so, that's the whole of my argument. They said, even if they hadn't explicitly colluded, they could have tacitly colluded. It's like the mind game, and I really think that was wrong. So I'm going to just move over here, and We don't have that much time, but here's some example. For instance, that the mind game, even when they're explicitly meeting in bars, this is what happened during the period of collusion. Here's the market share. Visi continued to increase its market share even when they were colluding. And I could hear this in the conversations. It's like they would have a series of auctions, they call them tenders, where they said, well, I'm going to bid this, you know, Visi bids this, we're going to bid this, and we're going to win that one. And then they would submit and they would agree on this. And then they would go and bid, and Visi wouldn't keep to its word. Visi would submit a lower bid and would win. And then you would hear them the next time, they would swear at each other. Say, you know, damn it, you know, we were supposed to win that tender. Now we want some compensation. And they're yelling and arguing each other. So even when they're explicitly talking to each other, you have cheating going on. And so, you know, Amcor is being taken for a chump. So anyway, what did we think that a competition should have been? It was before all this collusion, they were just doing leapfrogging competition. And so the idea is that you invest and then you're the low cost leader, and then you're going to get most of the market share at a low price. And the difference, your price will be, you're going to set your price as the low cost person just below the price of the high cost person and make all that profit until, for a certain amount of time, until the next your opponent, Visi, leapfrogs you, and then they're the low cost leader. So this is my conjecture of the a solution. And so I think we're going to play a little game. Yeah.
So what was the main argument of the other side? Why would that not be possible to?
Well, they said that, they said, you know, there's no evidence. You know, we know that people don't play Bertrand price competition. This, you know, and they said they would have tacitly colluded. And there's just a whole bunch of evidence from the laboratory. This is laboratory evidence, for instance. There's a meta-analysis of 510 laboratory experiments. In laboratory experiments, you can't get, when you're trying to see, will people, tacitly collude, they just can't get it to happen in the laboratory. It's very, very rare, and they try all sorts of designs. So here's one right here where they have a price ceiling. And so here's two different games. The darker one is where there's no price ceiling at all, and they allow them to collude. And you see that even though the collusive price is 48, way off this chart, what the players do is just very close to Bertrand, which is 21. So the prices are just close to Bertrand. Now the other one is they initially don't have a price ceiling. This is this purple line. Then they put a price ceiling of 28, and they say, is that a focal point for collusion? And initially, when they put the price ceiling in, it seems like they're going up, but then those prices deteriorate going back to Bertrand. So the bottom line is, I think there's very little evidence for this mind game of tacit collusion actually being a sustainable equilibria. And there's just often rampant cheating, even when you can communicate. And then this graph here shows that when you don't communicate, you can't really get collusion. But when you communicate, you have a better chance of being able to successfully collude. But tacit collusion is purely a mind game. And that's potentially illegal. If it's potentially legal. If you can just think and not explicitly meet in a bar, they can't say you're really colluding. But if you actually meet in a bar and talk and plan, that's illegal. So anyway, let's play a game. We're going to play a leapfrogging game now. So, okay. So why don't you set the model?
All right. So yeah, thanks. Sorry for kicking me out, John. So the experiment here is that now that we understand the process of leapfrogging and the competition between these two firms, let's try to formalize it. And then we wanted to do a little game so that once you know the Bellman equations and the whole structure of the problem, right? You are economists and well trained, you should be able to play this game and see how you do against the other competitor. But let me just jump into the program. So this is a stochastic dynamic game. We have two competitors, and that number is fixed, no exits or entry. Discrete time, infinite horizons. Just for simplicity, we're assuming that the discount time with the same discount factor, and we assume that there are I have a thing here. There are two choices, right? So each time period, the competitors set the price, but they also have to decide whether they want to buy that wonderful B9 plant, right? That's the state-of-the-art technology, which is in this setup developed by somebody else. There's no R&D. So there is Germany, where we are, which develops these machines, right? That John showed, click through the picture, which allow you to produce cardboard at the lower marginal cost. And so the choice is really binary. It's either you invest and buy this new machinery, or you just stay with the old technology. And then we also assume that the consumers are really static. There's no brand loyalty or anything. They just, every time period, they're going to buy from the cheapest producer of this cardboard, okay? And that allows us to actually completely hide this additional choice of price, because in every time period, we will have just a static Bertrand price competition, right? So we can write the profits of these two competitors right away. Now, let's think about what's important about these decisions. So what information do the competitors want to take into account to understand whether they invest in the state-of-the-art technology? Well, obviously, that's going to be the cost of that state-of-the-art technology at that time, right, when they're making the decision. We will assume that it starts at some initial value, C naught. You know, for simplicity, it may go all the way to 0, although of course you could have a lower bound. We discretize it with n points and model it as a Markov process, completely exogenous to the rest of the model. There will be an investment cost, and here we're going to set it as a function of this state-of-the-art marginal production cost. And this is what you have to pay to get the new technology, okay? And there will be one period of wait. So we're making decisions today, and the new technology comes online in the next time period. Now, what is the structure of this industry? Well, we have two firms. We have the state of the art. And so eventually we have to keep track of these three numbers, right? This is the marginal costs of the two producers, the state of the art cost, and that's all the information that we really need to know. Now, we have this natural inequality constraints. You know, the marginal cost that they are using in production right now cannot be lower than the best that is possible in the world, right? So it forms kind of a quarter pyramid, we call it, but we'll talk about that a little bit later. Now, we also assume, as you would expect, that there is private information in the terms of this stochastic components to the costs, which will affect the investment decision of the two firms. And with no surprise, they're going to be distributed with extreme value type 1. And we will have a scaling parameter, eta, okay, that scales up and down this random components in the cost function. And this way we can talk about sort of more or less noisy situations of this choice. And we'll get analytical expressions everywhere. I need to keep track of time. We don't have a lot of time, but you know, solving this model was very exciting. And we were sort of fighting for John's reputation, right? Because the other side said this is impossible. So we had to show, you know, with our own hands that no, it's actually possible. Leapfrogging is possible. So anyway, we have two versions of the model. One is with simultaneous moves, where the investments decisions are made in every period by both firms. And then for completeness, we also set up the alternating move specification. And here, unlike chess, when you know whose move it is now and next sort of time period, we have an additional stochastic process, which basically shows, you know, who of the two competitors can make the investment decision in each time period. And we can have a Markov process on top of that as well, to control that as well. So the actions are, you know, setting the prices and deciding whether to invest in the state-of-the-art technology or not. Because of the random components, this will be expressed with choice probabilities, which have the logit form. Right, and the strategy profile is a pair of these Markovian behavioral strategies, which describe the two actions of each player. And now here's the definition of the Markov perfect equilibrium. This is a pair of strategy profiles for both players and a pair of value functions which solve the Bellman equations of each of the player, right? Such that the Bellman equations are satisfied for each firm and the strategies constitute the mutual best response and also assign positive probabilities only to the actions in the action sets of the maximizers of the Bellman equation. Right, so we have to have these two things, that the Bellman equations are solved for this choice probabilities and choice probabilities follow from the solution of the Bellman equations. So in that sense, you know, this whole game literature is really just combining the life cycle models that we've been talking about for the whole week. So each company has a dynamic model to solve, right? This is going to be infinite horizon, but still. While taking into account what the other competitor, the other player is doing. All right, so let's just look at the Bellman equations because we need to formalize the structure of the model. Here's the value for firm I, and I'm gonna write this example for I equals 1. It's a maximum between two choices. I guess I kind of glanced over the over here. The expected one period profit is just given by this expression, right? So if you're a cost leader, if I is less than CI less than CG, then there is this profit to be earned by firm I in that time period. Otherwise, you're earning 0. And this is sort of separates from the rest of the model. We know the profit structure for each combination of the state variables C1, C2, and C. All right, so the choice is really between to invest in the state-of-the-art technology or not to invest. Okay, the choice specific values, both of them will have the current period payoff, which is just the profits from the current structure of the industry. If you're investing, then you're also paying this investment cost, right? And then there is a continuation value that corresponds to not investing or investing and starts from this current structure of the industry. Of course, we form the choice probabilities in the usual way. And now let's look at the expected values, which describe the future, the next time period. And as we just said, there are two of them for each player, corresponding to investment and not investment decision. So if I'm not investing and I'm firm number 1, that means that over here, this H function, which is the log sum, which is the expected maximum for me tomorrow, this H function will depend on C1 since I haven't invested. In the investment case, my cost goes down to C in the next time period. And over here, we also have the choices of the other player, and they control what happens to the C2, right? So if the other player invests, then tomorrow his the marginal cost of production is going to be going down to C, and so forth, and the same thing here. And finally, we have to take the integral over that exogenous Markov process of the improvements of the technology of state of the art, right? The technological process. All right, so you know everything. Yes.
But could it happen that both firms decide to move in investment?
Yes, absolutely.
Right.
Huh?
So what would be for both firms in the next period, their cost will be
equal.
Not lowercase c, right?
Yep. And then we look at this formula for the profits, right? So yeah, absolutely right. So this market is really contestable, right? Because in each time period with the simultaneous move case, they can both invest in the state-of-the-art technology. There's nothing to prevent the competitor from buying the same machinery. And that's bad, right? Because both of them paid the costs and there's no profits to be made.
So if nobody wants to invest, it's earning profits, why would they want to invest?
And that's exactly the point, right? So if that is a possibility, why would you ever buy any technology? You know, you're thinking, okay, I'm going to buy this new wonderful plant, hoping that I will be a cost leader for a sufficient amount of time to earn the profits to justify the investment. And this is what we refer to as Bertrand investment paradox, right? Because the competitor can do exactly the same and kill this whole plan. Is there an equilibrium in this setting? Let's try to think about that and try to find out whether we can beat the computer here. Okay. So I'll ask John to probably lead the process, and I'll be at the computer.
Okay, so we're gonna Fedor's going to start again. We're going to just play it all together, and you can suggest what you want. But there's going to be a voice speaking, and it's going to tell us when the state of the art. It's going to start at 5, and then at each time step, you can decide whether the firm should invest. So we'll be playing against a computerized opponent, right? And this computerized opponent is playing an equilibrium strategy. So we're going to, by humans, going to try to compete against the computer and see if we can beat the computer.
Okay, let's see if it works. No, I can't hear any sound.
Okay.
I'll be the voice. There's a nice, this is a terminal game, but it has a voice.
Yeah.
Welcome to the game. Here's the description of the industry. Can you see this, by the way?
Yeah, it's on.
Do you have the sound off of it?
Yeah, I think I just turned the sound on. Can I share the sound? How do I share the sound? Oh, there. Okay. Well, anyway, let me just talk through. So here's the state of the art cost. It's 5. Okay. Investment cost is going to be fixed for this whole game at 5.2. The current price of the products of the cardboard is also 5. Firm 1 is the competitor. This is us. We are at the very start. Production cost is also 5. We are starting from the very beginning. There's nothing better in the world to, produce current profits. We don't have any. There's cumulative profits and the discounted profits. So the question is, do we buy the new technology, which is, state of the art cost 5 at this first time period that we're playing? And, I hope Hans Martin will help me to set up a Zulip poll so that you can actually press yes and no. But here it's kind of, and this is for the online online participants as well. But think about, should we buy it now? So what happens if we buy the state of the art technology? The state of the art now is 5. And we have 5, so we will just basically lose the money on the cost of investment, right? So I think we shouldn't. Does everybody agree? All right. So here we have to import, enter the probability of investment. So I'll just leave it at 0. Okay, time period 2, and you can see nothing happened really. So there was no technological improvements. Nobody came up with a new machine. Everything is the same. We're not earning because anything, right? Because we are at the same marginal cost. What do we do? Nothing, just continue, right? Okay. And time period number 3, still no change. Just continue, right? Okay, let me move this window a little bit up. How do I do it? So that we can see better.
Scratch it down from the top.
All right, so we just stay there. And I guess we just continue doing this until something happens, right? And here it is, technological innovation. You can see that there's a new machine which allows you to produce at the cost of 2.0833. Okay? And this, the industry is still in the same state, and we have to decide, do we buy it or not? And now we can have a Zulip poll. And it went from 5 to 2.8. And the cost of buying this is 5.2. So kind of 2 periods will be enough, right? No, of course, discounting and all that.
We haven't told us the distribution of the cost, but probably it's going to go down again.
Yeah, okay. Yeah, that's right. That's right. Yeah, I could have told you all the parameters, but this is real life. You don't really know. Maybe you have done your research. Unfortunately, Philip is not here to talk about the ambiguity. So what do we have on Zoom here? 4 for yes, 5 for no. Oh, wait, there's another yes. Okay, it seems that we're converging to kind of 0.5, and I think that's all right. So does everybody agree? All right, so we decided to invest with probability 0.5. Okay, and we didn't make the investment, but the competitor did, unfortunately. So the structure has changed. You can see that now their production cost is 2.08, and we are at 5. Of course, they had to pay for it, so they paid the cost, but they've already earned some profits, right, to recover part of that cost. What do we do now? We can, in principle, punish them, right, by buying this technology and killing their profits, but that costs us too. Yes, there is a positive probability all the time. Yeah, I don't remember the specifications. Sorry. Yeah, I should have probably explained the probabilities. Can we have another poll?
Can you repeat the profit sharing scheme?
Oh, nobody is earning anything, right? It's a Bertrand price. So the price goes all the way down to the marginal cost of us both, and nobody's earning any profit. Okay, so here's another poll. Oh, people seem to converge at no. Okay, so then I put 0 in here. And so, yeah, we just stay with 5 production costs, right? The competitor is making profits. Is there any reason to change it now, or we just stay with 0? Stay with 0, okay. And see, their profits keep increasing, unfortunately. Right, so we're at time period 14. And yeah, all that's changing now is that they accumulate profit. But at least we are at 0, right? We didn't make any loss.
So this, in the counterfactual, if we had invested in the period in which technology changed, we would have both sustained losses over the entire period.
Well, just once, right? And then stay. Yeah, exactly. So in the counterfactual right here with this simulation, well, the game stops after, I think, 30 periods of nothing happening, but there can be still a technological improvement, right? No, okay, it just didn't happen. This graph shows us basically the time on the horizontal scale, and this is price and the marginal cost. The price is the red, no, the price is on the top there, right? It's it stayed up. Is it right? And the shaded area, anyway, is the profit that the other guy had made. But we could have had a different simulation here. So, do we want to play again, or just go on? You want to play again? Okay. Yeah, let's do one more. All right, we start at the same point, essentially, and we don't invest, right, in the beginning. No.
The technology evolution.
Oh yeah, that's right. That's a very good insight. Exactly right. So here we're playing the multi-step stochastic technological improvement. So there can be a sort of a drastic decrease in the cost of production, as you have seen. We can specify it in many different ways, and we will see, what implication it has to the solution of the whole problem. But I guess I'm staying at 0. And nothing happens. Period 7, and still nothing. All right, here's a technological improvement. That's we're in period 13. The marginal cost of production for the state of the art went down to 3.9 from 5. What do we do? Is that enough to justify the 5.2 cost? Sorry. Wait for the next, but they can, the competitor may invest now, start earning.
Yeah, we're probabilities here. Make those decisions under ambiguity.
Indeed. So what do we say? 8/5. 10/6. Okay, it seems that we should invest with what, 0.7 or something. And we used the 0.7 probability of investing. We did invest, as you can see. Now we're producing at 3.95. We sustained some loss, but we're now recovering it. The competitor did not make the investment, so now we are earning the profit on this market. And the price is still at 5, right? Because the top cost of production is 5, so the price cannot go down, but the rest is just our profit.
Does the computer know the profit? Like, does it know the technology?
Yeah, the computer does. All right, but look at this. So, we started accumulating some profits. We're making a profit of 1.047 in each time period. And I guess we are right now. We just recovered our investment cost, and I'll just stay like this. Oh, there's another improvement. Okay, now it's a little one. Right now it's from 3.95 to 3.75. What do we do? Oh, we have infinite horizon. The discount was, let's see. Yeah, maybe about 0.95 around there. Wait for the next shot. Yeah, Jay?
Questions. Do we have information when this technological change happens, like this?
No, we only know the transition probability, right? We're just waiting. Yeah. Eric, did you have a point?
I just said thumbs down.
Thumbs down. So we don't. Okay. So do we want another poll or? All right. So I don't know. What about 0.1? I mean, we don't want to let them to leapfrog us, right? Because they can become the cost leader, and then we're not making profits anymore.
But like also, like they're entering in a probability, right? So like presumably they're relatively unlikely to invest this time because of the
Yeah, that's a good point. That's a good point as well. Okay, so let's stay with 0.1. And there's a technological improvement again, right away from 3.75 to 2.9. And by the way, they did not invest, and we didn't invest, right? So the cost stayed the same. But now we have to make the same decision, right? Whether we go from 3.95 to 2.91. Yeah, sounds pretty good. Do we have a poll for that? All right, sounds pretty good. Okay, let me just make one. Okay, certainly investing.
Why are we making the poll then?
Say again?
Well, it's at 0.92 or something.
Okay. So look what happened here. So we've invested together with the other guy, and now we are at the same marginal cost of production. The price went down. That's good for consumers, right? But they're at -5. We're at about 1.05. I guess we're not doing anything now. Right. So we assume that there is no exit, right? So we're just gonna, keep them at zero profits essentially, as well as us. Was there another improvement? No. So we just stay as we are. Nobody is earning, but we're definitely leading, right? In terms of the profits. Nothing happens. Period 37. 41. 3. Oh, there's another technological improvement. Now it's from 2.91 to 2.29. What do you want to do? Okay, I'll wait for the poll this time.
What has been the average, roughly the average number of periods?
Oh, did you count?
No.
No.
something like that.
Yeah. Okay, so we are. All right, so let's just do the hands count then. Who would like to invest? Small fraction. I would say like a quarter. And everybody else would not like to invest? About the same number of people. So a lot of people are indifferent. Okay, so should I put 0.5?
I would not. It's like
It's quite small, is it?
very small.
It's a very small.
And then there's the technology. Like the cost seems very unlikely.
All right, so the poll is still not there. Okay, I'll just stay with what I thought was what I saw. And with 0.5, we did not invest, as far as I can see. Or did we? No, we did. We did invest, and they didn't invest. Okay, so we're cost leader now, and we need to hope that there's nothing happening so that we can recover the cost. The current profit is 0.62, right? So we're making 0.62 in each time period. And now we're above zero. All right, here's another one.
So did we break even now?
Yeah, we did. So, right, it's right there. All right, so now it's from 2.29 to 1.25, also pretty sizable. Yes. Yes. With like what, 0.9 or just certainly? Okay, certainly yes. Okay.
It's called reinforcement learning.
I would not.
Okay. So, yeah, I have to say the code is in the repo. You can hopefully run it on your MATLAB installations and check all the parameters. Yeah, sorry for not having them. So see, we invested together,
Yeah.
and so we are both on minus, but they're doing worse.
It's not right. Like it seems to not even like the computer doesn't really seem to be playing almost even a better.
Well, so.
Right? It just seems to be optimizing based on cost.
I have to check the settings, but we are actually playing with an easy strategy. We're playing with a mixed strategy where computer is not playing its best for sure. There is a way to set it up that there is no way to win, but I think we won the last time. I think we're doing pretty good now. So I think this gives you enough of a feeling of how it is, right? Let's go back to the model.
Can you continue so you can see the price tag?
Oh, okay. Yeah. So what are we doing here? Nothing, nothing, nothing. I think we have to have nothing for 30 time periods. There we are. So here's the graph, right? The firm 1 cost is red, and we are firm 2, right? Our cost is blue, and this is the profit that we made.
Black line is the.
And the black line, yeah, the black line is state-of-the-art cost. That's right. So there was that small improvement here that nobody decided to invest in. All right. Well, you got a feeling of how complicated, I guess that is, right? It's not very. Maybe if we spend a lot of time, we'll learn about the probability distribution of these technological improvements. Maybe we can do a little bit better. But let's try to solve the game. And what we have about 25 minutes, so I have no chance of finishing 160 slides. But this is really exciting. And the big picture is that, as Bertel explained with static games, the goal here is to try to solve this and see, whether we can or we cannot recover all of the equilibria. The equilibria are going to be complicated. but then hopefully we can still, derive an algorithm which is doing sufficiently okay, so that we can put the full solution into the, into the loop where we optimize over the parameter space, or the parameters. And that's actually what we're working on, but I don't know if we get to that point. So I'll focus on explaining how to solve this game for all equilibria. That's the first step. All right, so this is our state space, right? The quarter pyramid. On the vertical axis, you have the state of the art. And on the horizontals here, you have the costs of the two firms. We started every time from the top, and you can see that, this is the origin, 0, 0, 0. You can see that the actual costs of productions are always above the corresponding state of the art cost. Now, if we think about the layers of this pyramid, these are different state of the art costs, right? And so when technology improves, then we sort of fall through these layers. For example, we started the 555 on the top there, then we wait, we can spend some time in there as you've seen, then we fall through to the next layer of the state of the art cost. And here we could invest, one firm can invest, or two, or the other, or both. And these are the transitions. So imagine both firms were very eager for the technological improvement, and both invested. And now we are at this corner point where the costs are equal. And so they're all now 2 to 2 over there, it says on the top of the slide. We stayed there for some time, potentially, but at some point the technology improved again. And now we are on this interior point, colored in yellow, where again, the same type of choices. And imagine that only one firm invested from this point. Now we have a cost leader here. The structure becomes 1 to 1. One firm has the state of the art cost, another one is cost follower. And this continues, another technological improvement. And maybe this time the other firm invested and the structure became 1, 0, 0. And now the firm which used to be the cost leader is now cost follower. Right, so that's the notion of leapfrogging. These firms can become cost leaders in some control stochastic process. And this transition here, where the other firm, the cost follower, invests, makes very little sense, right? Because you pay the investment cost, but you're not going to earn any profits. We're going from 1, 0, 0 to 0, 0, 0. No profits in here, but this is the last kind of theoretically possible transition in our state space. And now you can see the main idea of the directional dynamic games. So these are going to be the games where transitions to the state space, they go sort of in one way. And there is a set of absorbing points in this structure. And I want to make this a little bit more general and put these layers, into one plane. And so each box here represents a layer in the pyramid. And here the errors, all these errors are showing all possible technological improvements. So this is when the game, the whole model transitions because of the technological improvement between these different boxes. Now let's think about some strategy. So let's say that firm 1 has a strategy to invest in all interior points. And this is just arbitrarily chosen, okay? So invest in all interior points means that if the game is in one of these yellow dots, then firm 1 makes the investment. And I've added the red lines, right, which correspond to the transition of the game in that strategy. And maybe the second firm had another strategy, also has a strategy, say, invest in the edge points, in the blue points on the edges of each of the layers. So now you have a strategy for both firms, a strategy profile, and each strategy profile corresponds to a particular picture of transitions on the set of all points in the state space, okay? And this is a partial order. So now we can formalize this and say, that what we can and cannot allow in these models. And for example, we cannot allow the loops under any feasible strategy. And that's that notion of directionality. So compare these two cases. First, the self loops are okay because we could stay in the same point for several time periods, okay? So this is what makes it not a DAG, but almost a DAG. But we cannot allow this situation where there would be a loop between different points. Okay, that's the anti-cycling no loop condition. Now we also want to require consistency between two different strategy profiles. So we don't want to allow the situation where under one strategy profile we have something like this, and under another strategy profile we have the opposite transition. Okay, and that happens to be the only conditions that we really need. So the directional dynamic game is a finite state Markovian stochastic game, which has these two properties. Every feasible Markovian strategy has no loops, and every pair of feasible Markovian strategies induce consistent partial orders. Okay. Now, if I draw all possible transitions in this leapfrogging game, this is the picture. Everything that happened in this game is drawn here with the errors. And I hope you have the intuition of how, it starts with the apex, with the top, and sort of slowly goes into this last point, although maybe these last transitions never actually happen because they don't make economic sense. So we are working with the DAG, and now what do we want? DAG is directional cyclical graph, right? There are no loops in here, and it's a directional graph. What we want to find a way to solve this problem in steps. And the idea here is that instead of, we want to use Bellman equation, essentially. We want to do backwards induction, but now we're working not with time that goes from, time period t to time period t plus 1 and so forth in a linear fashion. Now we have this complicated structure of transitions, but we want to find directionality. We want to somehow separate this into subsets such that there is a full order of these subsets. I'm gonna speak into the microphone and you'll hear me better. All right, so first of all, let's run this algorithm that partitions our whole state space into what we call stages. And the algorithm is very simple. You find the points where there's nothing coming out of. That's going to be a set of end game points, and you delete all the errors that connect to it and put it into a group. And in this game, this is just one point, but there could be multiple. We repeat the steps. Here's a number of points which don't have any errors coming out of them. We put them into a different group, and we call this group stages. And then we, repeat this process. And you can see that when we put a collection of points into a subset, then they also don't correspond between each other. But this is a finite process, or rather you can actually formulate a test, right? An algorithmic check of whether you have loops or you don't have loops. Obviously, if you have loops, then this will not stop, right? But now we have a collection of stages. And if I show all of the possible transitions here, you can see that the game transitions very directly from the start all the way to the end, and there's a direction, which stage comes before which other stage. Now we can talk about upstream and downstream stages. The game goes in one direction, and that allows us to solve it, right? So we first look at the very last stage. In here, all of the transitions, and think again about the Bellman equation. The Bellman equation was concerned about what can happen in the future. Well, here, nothing can happen except that you stay here, okay? You will, in this absorbing states, you will always be, should I close the door? Is everybody all right? Yeah, anyway. So here you know that nothing will happen in the future, no transitions, and so the structure of this game is fixed forever essentially, and you can solve it. It's not that hard. It's not a dynamic anymore. But now taking this solution into account, you can actually solve the previous stage by plugging in what's going to happen if the transition takes place, right? So we solve the Bellman equations here, and then the solutions of those Bellman equations become parts of these Bellman equations. And we sort of plug those solutions in, and we continue doing this. And essentially what we're doing, we're following the order of the stages, which is a full order, in the backward induction manner, right? So we separate the stage, the set of the points of the state space in this problem. We separate it, we partition it into a collection of the stages, and we find the total order on the stages and follow that backwards. And that's the notion of directional game. And this algorithm we call stage recursion, right? And you can say that this is basically a generalization of backwards induction. You have to keep in mind all the time that in each of these points in the state space, we could spend a long time. And we saw that in the simulation. So this is not about time. This is about transitions through the state space. All right, so now we've solved the game. This is a summary of what I was just explaining. And you can compare that to the normal backwards induction where the time has a very simple DAG, right? It just goes from period 0 to period capital T. All right, now I have about 10 minutes, but I'll try to push on and then allow, let you see the slides, the rest of them by yourself. What are potential problems? Well, let's look at this very small subset of that state space in the very end. Imagine that we have one solution here, and then we can plug it into all the upstream stages. And we may have one solution. That's actually what the case is, right? For the corner solutions and the edge points, you have a single solution. But then suddenly in the interior point, you may have 3 solutions, or in fact 5. The question is, what do I do here? Right? Which solution on this stage of that subset of Bellman equations that correspond to that stage, which solution do I use upstream? Okay? And that's how multiplicity starts get in the way. We basically came up with this, what we call recursive lexicographical search algorithm. And we thought that was a very cool idea and a fancy way to solve the problem. But then it turned out to be a quite simple thing. That's the process of research. You're solving a particular problem, and then sort of as time goes, you realize that it's actually maybe it's already solved problem, and maybe it's actually not that hard to do it all. But here's the sort of typical picture of the stage, and we can have one solution, 3 solutions. These are best response functions for the case where eta is equal to 0. And on the axis everywhere, we have the choice probabilities for investment. We have this very linear or piecewise linear best responses. That's because firms know exactly what to do. There are no extreme value shocks. But you can have a situation like this with 5 equilibria on the stage, which creates the multiplicity. All right, so here's the original idea. Let's just write a long string of numbers. The indices here from 1 to 14, they index all points in the state space, okay? So if the game is large and it's discretized in a fine manner, then this is very long objects. But for the example, let's keep it like that. And now it is also important to realize that we index it in a way that is shown where? Here. Here are the indexes of the stages. We arrange them in a very specific way. So number 14 is going to be the end game, the absorbing state. Number 1 is going to be the most dependent state where things could go wrong, right? And so number 1 goes here and 14 goes here. And that implies, right, that the solution on this side of the problem will influence, the solution on this side of the problem will potentially influence these digits, but not the vice versa. Okay, here's the idea. We can write all these numbers. Oh, in this indices in here, they correspond to the potential multiple equilibria, potential multiple solutions on the stages that we just enumerated. We can write this. Wouldn't you agree? We can just write a big table of possible selection rules for the equilibria. So basically this says that I'm selecting equilibrium 0 on stage 14, or in point 14 rather. You can see also there the points are collected into stages. But anyway, so I'm selecting equilibrium 0, index 0, and so forth. And over here, say I'm selecting the 3rd equilibrium and the 3rd equilibrium here and the 1st over there. So by fixing this string of numbers, we can actually prescribe, going back here, we can prescribe which equilibrium we're taking from each points of the states when we do the backwards recursion, the state recursion. So in here, for example, this would be meaningful, right? We need to know which equilibrium to use to calculate everything upstream. But where you have unique equilibrium, then it's just easy. So is the idea kind of clear? Hopefully. Well, the problem is now that a lot of this makes no sense, right? So if we said that we're going to select equilibrium number index 2, number 3 on this particular point of the state space, maybe there's a single equilibrium there. So we don't need this line at all. So there is a task of kind of searching through this huge table for the strings which actually correspond to the multiple equilibria on the stages in our big dynamic game. But in principle, we can enumerate all of them, right? We definitely know that all equilibria of the big dynamic game, if there is multiple of them, will be in this table. And that's good to know. Now, the algorithm that we have in the paper has to do with variable base arithmetics, which is a kind of fun application in economics. You can be smart in about how to go from one line to the next line and sort of jump over the lines that don't correspond to the actual equilibria. But you're doing some kind of a search. And this equilibrium selection strings, they are ordered in the lexicographical order, and therefore the name. But it turns out that, and here's the algorithm. The algorithm is very, very simple. You start from the 0th selection, and then you calculate the basis for the next number, and then you just add 1 to the current ECR to find the next one. But it turns out there's a better way, or a better way to explain it possibly. So if we also use the same indices as we did before when we were writing this table of equilibrium selection strings, and have the point number 1 over there and the point number 14, and this is, right, remember the 14th is the point on which everything depends, but it is most stable. Then as we solve the problem, we can kind of notice where there would be multiple equilibria in the stages. So we're doing backwards. We're doing state recursion, we're solving the problem, and we just sort of make a note of where there are multiple equilibria. There are multiple here, here, and the first time we do it, we just take the first equilibrium out of that 3. And essentially what we've done is we've traversed the tree of equilibria all the way to the last node. And to find the next equilibrium, what you have to do, you basically go, where's my pointer? Go from this one back to the previous point in the state space where there was branching, and continue with the next branch like that. Okay, and then you repeat, and then go back to the next branch. And essentially, what you're doing, you're traversing a tree of equilibria. So the realization that we got after some time is that all of this equilibria form this very nice tree, which is not that hard to just go through. Okay, and so this is the full enumeration of the equilibria in this leapfrogging game. And so here's the main result. Assume there exists an algorithm that can find all Markov perfect equilibria in every stage game of the directional dynamic game. Then we show that RLS algorithm will find all of the Markov perfect equilibria in this big dynamic game of leapfrogging. There's a weak version of this as well. You need to recover at least 1 equilibrium in each point in each stage of the big dynamic game, and then you will recover at least 1 and potentially multiple equilibria in the big game. Now I have about 5 minutes. So there are some runtime numbers and sort of the boundaries on the number of equilibria. And you can see N denotes how many grid points we're using. And if we're using 5 grid points under the assumption that each point could potentially have 3 solutions, 3 equilibria, this is the number of the total number of equilibria in the game, potentially, the upper bound. That's the number that includes all of them, okay, in that big table. And here's the actual number of equilibria. So we have this example with almost 200 million equilibria in this leapfrogging game, and that's using 5 points to discretize the costs. And it took us about 45 minutes to compute that. So you have to solve under every selection string of the equilibrium. There are many selection strings, so there's many equilibria to combine to solve, right? But then you go to a slightly different formulation. That was the simultaneous move formulation. You go to an alternating move simulation with certain parameters. And your upper bound is the same because nothing really changed. It's just the alternation. But it turns out to have a single equilibrium, and we have a theorem in the paper which specifies under which conditions that happens. And then you're done in 0.006 seconds. The point of this is to show that that search part of the RLS search algorithm is really efficient. You don't spend time at all to go through this number of potential equilibria, right? You just get to the equilibrium that you have, and you immediately know that that's the only one. Okay, now we have the issue with this whole approach is that you have to have the algorithms to solve the stages. Okay, and that's in general, that's a nonlinear system of equations, and we don't have a surefire algorithm to solve a system of nonlinear equations. In practice, of course, we can solve them, but we have a couple of theorems here showing that with eta equals 0, you actually do have a finite algorithm to solve for all equilibria in every stage of this big game, and there can be up to 1, 2, 1, 3, or 5 in the simultaneous move formulation, and 1 and 3 in the alternating moves formulation of the game. All right, so I guess I have about 2 minutes, so I'm going to skip through a lot of this, but let's look how the equilibria, can be mapped in that game that we just played. So here is the payoff map. On the horizontal axis is the profits, discounted profits, right, of one firm, and the discounted profits of the other firm. The 45-degree line shows you the maximum profits that can be extracted on this market. And we keep the assumptions on the demand intact in this whole exercise. Okay, so nobody can extract more than the firms just can, share that maximum profit, which corresponds to a monopoly. Well, what you see here is that under this exact formulation of the game, under certain parameters, you have equilibria, which are MP equilibria, where one of the firms makes all of the profit and the other firm makes 0 profit. And these are in the corners here. And this is simultaneous move version. And you also have an equilibrium where none of the firms makes profit in the long run. So this is the result that shows you that this very simple extension, or seemingly simple extension of a Bertrand price competition with this very simple, additional possibility to buy a technology that is produced somewhere else exogenously completely, immediately creates the structure where you can have the Bertrand competition results, sort of no profits and the prices are down. Or you can have the monopoly outcomes being supported as the mark of perfect equilibrium. Now, this is for the deterministic technological change, okay? Here's the picture for stochastic technological change. And each dot here maps a combination of payoffs corresponding to one of those, I think in this example, 200 million equilibria that we computed. And, they pretty much fill the triangle of possibilities, so. Now we can look at the differences of different formulations. And so over here, I have the simultaneous move game with the deterministic technology. And this is how the payoff maps for the alternating move game looks. And in general, we get less equilibria in the alternating move as you would expect. And also we prove that in this case, the 0-0 profit outcomes or the monopoly outcomes are not supported. Now you can talk about the efficiency of this equilibria. And here we're able to plot the empirical CDFs of equilibria. There are so many of them that we can, look at the distribution of the efficiency measure across all possible equilibria. And we know that, for example, the mixed strategy equilibria never comes to be efficient. Never comes to efficiency 1. But in general, in this example at least, the equilibria seem to be pretty efficient. This is simultaneous move starting from about 0.88%, and the alternating move, it's more efficient, above 94% of the maximum social surplus that can be sustained in this economy. I guess I have to stop. But let me just preview of what's going afterwards. So we have several examples of simulations where we simulate the full preemption and rent dissipation. So what's going on here? One firm never invests, that's the green line. the other firm, the red line, invests a lot. This staircase here, the black line, that's the deterministic technological improvement. It makes one step in each time period, and it's very predictable, right? And the monopoly on this market would invest with the blue line. And so you can see that in the duopoly case, there's too much investment, and therefore you have rent dissipation. They invest so much that they spend all of the potential of the monopolist on these investments which are too frequent. Now, you can have underinvestments compared to the monopoly outcome. You can have leapfrogging. So, this was the end goal of the project. We show that the leapfrogging equilibria are actually typical equilibria of this massive number that we find. And they are possible under various conditions. So what are the conditions here? We get leapfrogging under random alternation of moves. This is random one-step technology. So this is the example where the technology can stay the same, at least for 2 periods before going down, right? And the message here for this model is that every time you have a possibility of not perfect coordination between the players, I think that's the message, right? Then there is a possibility for them to start leapfrogging. All right, and then we also, because we solve this problem completely, we can check some of the assumptions. For example, if you assume that the players are symmetric, right, which is a quite typical assumption, and symmetric in this sense, that the value functions are can be found for each firm in the same way by just flipping their costs, then this set of equilibria out of the full triangle happen to be symmetric. So potentially you're losing a lot of equilibria. And then we also talk about the potential homotopy approach. So here on this graph, we have on the axis, we have the size of the scale parameter for that for the extreme value shock. And imagine if it's large, right over here, somewhere here. That means that firms don't really care about the economics. They just flip a coin. They're making choices really randomly. And you would expect to be a single equilibrium in that case. Everybody's just flipping a coin and making random investments. But as you start decreasing this scale eta, then you get more and more of an importance of the costs and the cost structure and the preferences. But see what's going on. As you move just a little bit from here to here, suddenly there are 3 equilibria. Right, so this map was drawn by solving this model many times to different levels of eta. And as you move eta down, then you have this explosions in the number of equilibria. And we actually made a movie. You can go to YouTube and see how, as you move different parameters, this payoff map starts exploding. All right, so let me skip all of this. And this is where we're going, right? This was the end goal, full solution estimation. The main point to make here is that, as Bertel already previewed for the static games, if we write the likelihood function, we have to actually look at the set of equilibria that are supported under a particular value of parameter, and then take the maximum, the equilibrium that corresponds to the maximum likelihood produced by the data for those choice probabilities. And this is a hard problem, particularly here where there are so many equilibria. The approach that we're taking is to separate this optimization problem. We essentially have a discrete parameter, right? This selection of the equilibrium. So we can still separate the problem into the outer loop where we maximize with respect to structural parameter theta, and the inner loop where we solve the model, but by applying, old methods such as, for example, branch and bound, we can solve the problem only partially while finding the equilibrium with the maximum likelihood, sort of while doing the solution where you don't have to look at the equilibria that don't appear to be likely given the data. Let me stop here. Very, I don't know, hopefully I got across the message that we're very excited about this. Questions?